This is the second section of Chapter 5, and it covers just two different kinds of distributions, neither of which we've looked at before: binomial and Poisson. A binomial distribution can be identified by the fact that it has four properties that are unique to a binomial distribution. First, the experiments, or the distribution problem, consists of a sequence of n identical trials. N is a variable number and could be anything from 1 to infinity. Two outcomes, success and or failure, are possible on each trial. Success and failure is the same as true and false, yes or no, any two. But that's all that can be the outcome of a binomial experiment. The probability of success is denoted by the letter P, and it doesn't change from trial to trial, and the trials themselves are independent. Our interest is the number of successes occurring in whatever number of trials that we are conducting. And to do that, we let x denote the number of successes occurring in our fixed number of trials. On the next slide, we've got the formula to calculate the answer, but the truth be known, it is an involved formula, and in today's day and age, most people would use Excel or another software package to calculate the answers to binomial experiments. In this formula, x, or the function of x, is the probability of x successes in the n number of trials. N, of course, is the number of trials. P is the probability of success. You notice n factorial is on the top, or numerator, of the fraction, and you remember that the exclamation point denotes that it is a factorial number. If the n was equal to 3, n factorial, just as a reminder, would be 3 times 2 times 1. So the binomial probability function is something that can be calculated manually following this formula. If you do that, what you'll have is the number of experimental outcomes providing exactly x successes in n trials. And from the second half of it is the probability of a particular sequence of trial outcomes with x successes in n trials. And that's the second half of this equation. To look at an actual example of this, take a look at the Evans Electronics firm. They're concerned they have a low retention rate for their employees. In recent years, they've seen a turnover of 10% of their hourly people on an annual basis. Thus, for any hourly employee chosen at random, they estimate a probability of 10% that the person will not be with the company next year. So we're going to choose 3 hourly employees at random, and the question will become, what is the probability that one of them will leave the company during this year? Now, we're going to let P equal 10%. That's the probability. N is the number of people that we're checking. X is the question mark that we're asking. Before computers were popular, tables were developed by mathematicians and published so that you could look up an approximation of the answer to the binomial experiment without going through the extended calculation. You can see in this table, if you look at just the portion, that N3 has been circled in red. We've identified that as the number of trials that we're going to have. X is the number of people that we're going to experiment with, we want to know about, and so that is in the X column. Along the top, horizontally, are the various probabilities that we're concerned about. And so when we go down the n column to 3 and the x column to 1, and then across to the probability problem of 0.1, you can see that the probability out of 3 people that one will leave over the next year is 0.2430, or a little bit over 24%. For a binomial distribution, there's some things that we know. The expected value in a binomial distribution is equal to the mean. That's what the Greek U stands for. The formula to calculate that is n times p. You'll have a chance to do some of these when we do the instructional video. The variance is signified by the Greek O at the tail on it, squared. O squared is equal to n times p times 1 minus p. So what does that mean? In the example that it was a 10% probability of success, in that formula, n would have been 3 because we were looking at 3 people. P would have been 10%, and then 1 minus 10% would equal 90%. So that's what our formula would look like. The result of that formula would give us the variance that we could expect. Taking the square root of that variance, of course, will give us the standard deviation. So to do the actual math, the expected value then, 3 times 0.1 is going to give us 0.3. The variance, to follow through on what we said, is going to be 3 times 0.1 to times 0.9, or 0.27. And the standard deviation is going to be the square root of that, which calculates out to 0.52. All of the things we've just talked about are necessary to calculate anything you want to know in a binomial distribution. Now let's look at a Poisson distribution. A Poisson distribution is often used in estimating the number of occurrences over a specified interval of time or space. It is a discrete random variable that can assume an infinite sequence of values from 0 all the way to infinity. Examples of a Poisson distribution in a random variable could be the number of knotholes in a piece of pine board. Not that you really care about it. The number of vehicles arriving at a toll booth in 1 hour. That could be something you need to know if your responsibility was staffing up the manual toll stations. You don't want to have too many people, but you want to use the probabilities to staff those manual toll booths to the point where cars are not being delayed too long. 2 properties of a Poisson distribution. The probability of an occurrence is the same for any 2 intervals of equal length. And the occurrence or non-occurrence in any interval is dependent on the occurrence or non-occurrence in any other interval. So the formula, again, a little hairy, more hairy than the first one. The probability function of x occurrences in an interval. The little Greek U stands for the mean number of occurrences in an interval. And E is a trigonometric function similar to pi in geometry, but the value of E is 2.71828. That's a rounded number. And so here are the different denotions of the values in the formula. The function of x, the mean, and the value of E. An example of this would be a Poisson distribution at Mercy Hospital. Patients arrive at the emergency room on the average of 6 per hour on weekend evenings. What's the probability of 4 arrivals in a 30-minute period on a weekend evening? And so when we want to calculate that using the probability function, what do we learn? If they arrive 6 an hour, we got to be careful to convert that to 3.5 an hour, because even though it's 6 an hour, we're only being asked about a half an hour period. X is equal to 4, that's the number that we're interested in. Following the formula, filling in the numbers and doing the calculation manually, we would come to 0.1680 is the probability of 4 arriving in the 30-minute period. As you can see by what's listed below, we could do the same calculation by using Poisson and then just entering 4, 3, and the word false. Why false? Because we were asked for exactly 4 arriving in a 30-minute period. If we were asked for 4 or less, then we would want to know the probability of 4, of 3, of 2, of 1, and 0. And we'd want to add all of those together. But in this case, we were just asked for the exact number of 4. That's why we use false. If we were looking for an aggregate number instead of false, we would have entered true. So here's the same thing that we were talking about, number of arrivals in 30 minutes. You can see the sequence goes on, and as the numbers of arrivals go up, the probability of success happening gets less and less. A property of the Poisson distribution is that the mean and the variance are equal. They're showing you that here, but again, we're going to do our calculations in Excel. The variance for the number of arrivals during a 30-minute period, in this case, if we did the calculation, it would be 3. So that covers the basics on both binomial and Poisson distributions. And we will now move on to the last chapter in the text, which is chapter 6.